Okay, hi and welcome to part 8 of our tutorial. Yes, it is part 8. Now, what we're going to do in this part is finish off the PCB. Oh, it really annoys me why I can't zoom in halfway there. Can I not zoom into like 200,000? No. Okay, fair enough. Right. Well, so if I turn on the rat's nest, then that's what needs to still be connected up. Oh, by the way, when I was talking about the switch, and I said in the last talk, I was saying, well, I said, oh, there's a problem with this footprint, which and then I never said, and I said I'll show you in the next video. Well, the problem is that because these pins are both named 1, it means they both have to be connected up. When we know that actually these pins are internally connected by the component. And that is a bit of a problem with Kicad. There isn't really a way around it at the moment. That if you have a component with internally connected pads, there just isn't a way around it. Other than no, there's just no way around it. Other than not labeling them as pads, I guess. Not giving them numbers at all. Maybe that would work. In any case, so what we will have to do is connect both of them, and to do that I'm just going to bridge them. So now they're connected so that Kicad won't complain, you know, that pin isn't connected. Let's just connect these up. Actually, you know what, let's rotate that round since then that's in the right place. Just change the grid, it's kind of in the way. Should stick to some metric, I guess. So I'm just pressing X to connect these things up. By looking at this, I can probably connect up that VCC without actually having to cross over there, because we can move this so it goes through there. These are they're quite close together actually. I'm going to move this up a little bit. Oops, I meant to drag it up with G, because I want to make sure that they stay the same. Because in our design constraints, and this is the first time I'm talking about that, I know that the PCB manufacturer actually has a minimum foot spacing for silkscreen of 0.15 millimeters. Which is actually the width of that line, as far as I'm aware. I'll talk about how you set sort of design constraints in a bit. Now I'm just going to reroute this wire through here. I'm probably going to adjust all this later, but one way to do that rerouting is what you can do is, if I just right click on this track, I can break it there, and then if I delete this segment, you know, it's deleted it where I wanted it to be deleted. Let's break it here and delete this segment. Just right clicking. Now if I press X on the corner there, I can now connect it up. So now we can pull VCC to VCC without any crossing over. That's that switch done. Let's do the other switch. I'll turn off the rat's nest. Turn that off as well. So local rat's nest. What are we going to do? And that's obviously got to go to that line. So I'm going to rotate that one round. And now that's that connected up. And actually, on the rat's nest now, all we're left with is ground, as far as I'm aware. Yeah, all we're left with is ground. If there's anything that isn't ground, we'll find out. Oh, there's a VCC there. So we obviously need to route all of the VCCs through to our power header at some point. And that is, oh, our XOR input is there as well. And the XOR input goes to, needs to connect to there. Yeah, that's correct. Because there's two XOR inputs, and that's one of them. Now looking at this, there's no way we can get through to there without crossing over our tracks. So what I will do is place a via. Now a via is a hole that's drilled through the board and then filled with solder. So this is a two-layer board. It has a bottom copper layer and a top copper layer, and that hole that's drilled through and filled with solder will bridge those two layers together. So we're going to create a via in order to get through to that pin. And to create a via, I just press V. I can also click and select place through via. But if I select V, I can then go through here, and because that's a pad, a through hole anyway, that will naturally be effectively a via anyway. So they are connected. Now one of the goals, what's that doing there? Suspicious. Must have accidentally put that there. What was I saying? One of the things that people often do is they'll often use the bottom layer as a ground plane, and they'll try and put all of their routing on the front layer or one of the layers, and then use the other as a big ground plane to try and sink any interference as soon as possible. So they'll minimize these kind of vias, and really you want to minimize vias and minimize crossover, because typically that will lead to a more sensible layout of the board. Really you want to make the track lengths between the points as small as possible as well. Avoid right angles, because the electrons bounce off the end, and if you look at how some antennas work, they actually work by forcing electrons, like setting up resonance and forcing electrons to fly out of the end of effectively a piece of wire and turn them into photons. So you don't want to do that. You want it, really you'd like these to be curved, you know. So but Kicad doesn't do curves, and not many tools do. There are some tools out there which do curves. People tend to avoid them anyway and just do tracks like this, but curve would be ideal. Okay, so what else needs to be connected up? We need to get VCC to our VCC pin. Now, okay, if our pin header is there, we would have to go through there again. I'm not going to create another via just for that. I mean, is this a sensible place for the power header? I'm not sure it is. Let's just put it there for now. Yeah, okay, let's leave it there. Right. And I need to connect to there. Well, I can go around this way. I don't want to do it on the bottom layer. Change to the front layer. So you can change the layer that you're working on here. That's just the front copper and the back copper. You can change it here as well. You can press minus. That will also change it. Now, ground. All our grounds are going to be on the back layer. Now we're going to do a copper fill to try and make the back layer, most of the back of the PCB, full of copper. But it's kind of useful to just connect everything up anyway, so that all the design, when we run this, which is design rules check, that they actually pass, and Kicad knows that everything is connected up. I need to see the rat's nest to see what's going on. Because we're on the back layer now, we can almost do whatever we want. So let's just connect up all the grounds on the back layer. Okay, yeah, what's that? Oh, that's one of the XOR inputs. So we've still got to do the 2 XOR inputs. Let's do the grounds first. Okay, why is there still a rat's nest there? Let me redo that. Sometimes you've got to make sure that sometimes it does sort of strange things and doesn't remember that you've connected it up. So where are we? VCC, pull high. Oh yeah. So pull high also needs to connect to there. And this is where, so how are we going to get there? I don't really want to cross over. Don't want to do another via either. Let's just do something a bit bonkers. I don't want to wait, like spend hours thinking about routing this. I'm sure you can do a much better job than this. Sometimes I think when these rat's nests still show up, because we've actually connected that now to pin 14, if that happens, what I usually do is run the DRC design rules check again, which lists unconnected, and that usually then sorts out any time where when you still see a rat's nest, even though you've just connected something up, then run that design rules check, and it usually gets rid of it. Right, let's carry on with the grounds. So bottom copper layer again, and the VCC there. Yeah, we do need to get a VCC up there at some point. And it looks like it's quite difficult to get a VCC up there without a via, because we've basically got to cross all these tracks. Let's put a VCC up there. We've already got a via here, which means that when we do our copper fill, that will have to be excluded from copper fill, because our copper's we're gonna connect that to the ground net. So if we put the via then from the VCC down here in the same area, then we're kind of minimizing the breaks in the copper. So I just need a VCC. I was already on this layer, I may as well stay on this layer, you know, and just actually do the whole thing on that bottom layer. Okay, so we've now connected the VCC there to the top. And we can carry on just using the front copper for the VCC here. I can go through here to that VCC. They are connected now. Let's carry on with the grounds as well. So if you just go along doing this. So this is what you end up having to do is just connect everything up like this. I've got another VCC there. And some more grounds. So as you can, hopefully you've been able to see that it isn't actually that difficult to lay out a board, even one with, you know, a lot of through-hole components. I mean, this probably isn't a lot, you know. Some people probably look at this and think, what's this guy talking about? This isn't a lot. If you notice, I've got right angles here, but they're connected to a pin, so those right angles aren't really going to make any difference, because in a way everything is a right angle that will connect to a pin no matter what angle you come at. so you can't really do much about that, and the via is always a right angle. I mean, the whole right angle rule, I don't know, I'd like to see some kind of empirical evidence about how it would affect a circuit, especially a circuit with low frequency noise. So some of the satellite transmission systems, they effectively have a big rod, metal rod, which electrons are in a way accelerated through or resonate in, and then the electrons fly out the end of the metal rod, and some of them reflect, but some of them fly out and turn into photons. I guess if you have at the end of a wire as a right angle, there is a chance that they will reflect, or or even be absorbed into the PCB, I guess. But I don't know practically what effect it actually has. I've not experimented with this myself. For a circuit like this, considering I laid it out on a breadboard with really crappy wires and awful connections and everything, and it works, I don't think it would make any difference. But don't take my word for it. Try and avoid them anyway. Let's carry on with this. I'm just going to rebuild the rat's nest. Because it for some reason doesn't think that the VCCs are connected, but it might be because it's not connected somewhere else. Carry on with the grounds for now. So we can see we're slowly kind of getting there in terms of the connectivity. There's just a few things left, which is nice. Okay, this is a ground there, that's fine. Right, it looks like we've only got a few pins left now. Just want to rebuild do a DRC again. Yeah, there's just a couple of things left. Now why is it saying, so it's saying that these are not connected to VCC, but according to our calculations they are. Wait a minute. See, I don't understand. So sometimes you'll get something like that and you think, well, why is that not, why does it say that isn't connected? We've got VCC going down here, over here to here, and okay, our power input goes through this passive here into here, so we don't actually have a direct connection to VCC, to that grid by the looks of it. So let me place another one on the bottom. I'm trying to go to the capacitor for some bizarre reason. No, we do. So from VCC here, we go through here, via that pin, and up there. So they should be connected. Oh, okay. It's just this net on the left that is not connected. It has no connection to VCC. So this net on the left needs to be connected to VCC somehow. Where is the nearest VCC? And that I think that rat's nest line there, it actually shows the nearest VCC. Is there any way we can do this without crossing over? Probably, if you think about it, you might be able to find a way. But let's just finish this off. Otherwise we'll be here all day. Now that really should be connected if I redo this. Yeah, that's disappeared now. And the only connections we've got left, we've got one of our XOR inputs there, which is needs to go to there, and then the other XOR input, it looks like it's already connected up. How are we going to get to there? We're going to have to use a via, but there's quite a few vias in that direction anyway, in that area anyway. Let's use a top layer from here. Just press X. We'll go through these pins. Now, going through these pins, what we'll do later on is we're going to change the width of some of these traces to make them a bit bigger. You could do that at the start, but for whatever reason, I've only made a few boards and I've just always done it this way. But probably it's better to select wider tracks to begin with rather than having to go and change them all. Let's place a via there to go through there, and we can obviously go straight to that pin because we're on the bottom. And just rebuild the rat's nest. Compile rat's nest. Okay, so you do have to do that if you want to rebuild the rat's nest. So now everything is connected up. According to the DRC, everything is connected. Now what you'll see also on the DRC is you can set some design rules, like the minimum track width in millimeters, the minimum via size, and so on. Now where would you actually get that information from? Well, let me show you where you might get that information from. So I've just been watching some things. This guy is a great guy, by the way, Robert Murray Smith. If you're interested in sort of chemistry and doing things at home, he's got some fantastic tutorials about how to, build graphene, usually graphene-based things. He's a really awesome guy. Just go check him out. Okay, so where I got my PCBs made recently was a guy called Hack Varna, and this is his guide. Then if I go to the bottom of his guide, he's got a kind of specification sheet, and what this will say is minimum line spacing, so it's minimum line spacing and minimum line width is 0.15 millimeters for this particular PCB manufacturing service. And the drill sizes, we've got 0.3 to 6.35 mil standard, or we can have smaller ones for an extra fee. And he lists a hole tolerance there, so they might mess up when they're drilling. So you've got to take that. You should probably take that into account when designing it. Don't put anything closer than 0.09 millimeters. And we've also got the solder mask, which is another. This is for the pads effectively. So this is where you don't want to have on the top of a PCB. You'll see like green colouring or whatever. Then that covers up the tracks and everything. And you obviously need to leave the pads exposed. So this is saying that the minimum exposure would be 0.1 mil. That's very small, and the clearance is 0.1 mil. The silk screen is the drawings that are on top of the PCB, all this blue stuff. So that will usually be rendered. You can choose what's rendered on that layer when you export it, but that will usually be printed on top of the PCB, on top of the solder mask, so that you can see, oh, I've got to put an R10 there. So if I look at this specification, the minimum line width for the solder mask is 0.1 mil, and the minimum clearance is 0.1 mil, whereas what they're recommending is 0.15 mil. So this is important because when you import stuff into PCB New, sometimes, like, if I look at this, that looks very thin, where it says LED there, and looking at it, the thickness is 0.08, so it's very close to the tolerance, whereas we know our tolerance is 0.15. So I would actually then change that. So it's important to know what the kind of specifications of your PCB manufacturer are in order to select the right values. Okay, so that is essentially all laid out. And if we look at all the design rules pass. So yeah, I'll just briefly say, so where would you put all these things? Minimum track width you can put in there. Then if you go to preferences, which is, where is it? Yeah, sorry, if you go to the design rules again, and global design rules, then you can see the minimum allowed values: minimum track width, minimum via diameter, U via diameter. Whether or not, for example, whether or not they allow buried vias, you'd have to ask if your PCB manufacturer if they do. Now that's okay. The defaults are usually okay. You can add custom track widths. What you'll notice is by default there's only one track width, which is 0.254 mil. I can't actually select any others. But if I wanted this to be thicker, we'll do this in the next tutorial, but you can add in here, I could have a 0.5 mil, for example. And then that would appear in, I could, for example, select track width 0.5 mil and make it wider. What else is there? You can add, so with the design rules you can add, although we just added in a thicker thing, this will inherit the general settings in terms of the width, but you can add in another net class, and you could have it for that particular net class. You could change the clearance and so on for that thing. So if we wanted to add in thick lines or whatever, and it needed, pretend it needed a wider clearance, then, but everything else was the same. And then if we do that, we would change the membership of our components, of our nets. So if we wanted VCC to be the thick one, then I can select it, change this to thick, and move it over there, so that VCC is a member of thick net class, not the default. Which means that VCC, anything connected to VCC would have that track width and would have that clearance. So if I run the DRC now that I've set that up, there's no errors because it can't have more than that thickness. But if I now try and connect to VCC, even if I use net class values, I was expecting that to be wider. Okay, yeah, sorry, I worked out what happened. When I edited the design rules, I didn't save, I actually pressed cancel, whereas I was supposed to press OK. Now that VCC is a member of that other net class, which has thicker track width and these parameters, you can see that the actual wire comes up thicker. If I run the design rules check, there's actually an error now, because I said that I wanted a larger clearance for this track. I can see that that's too near, so I can drag that away and run that again, and there's no problem. So in that way you can create different rules for each of the nets, and a net is a set of connected wires, and that's how you sort of select how you set your design rules for your PCB manufacturer. Okay, that's it for this tutorial. In the next tutorial we're going to do a copper pour, and we're going to just finish a few things off, and then after that we'll export the files for how you'd send them off to the PCB manufacturer. By the way, one more thing I want to say is, and I'll say this again probably in a couple of videos time, is when we designed our footprints before, like the one for the switch, a good idea is to print off the PCB. So if you print off the design, then you can actually check that these footprints are in the right place. So you can get your component and put it on top of it and check that it's the right size. So then you don't have to worry that when you go and get this thing manufactured and it comes back, that your footprint design was wrong. So it's a good idea to have the components you're going to use, print this off, and then physically check that they match up, that the footprints match up with your component legs. Okay, that's it for now. I'll see you in the next video.